Welcome to Hartman Math. Today we're going to look at transformations. For that, go ahead and take a look at our piecewise function. Do parts A, B, and then C, which is to graph it. Pause the video here until you're done. All right, so for part A, f of 1 satisfies this condition. We'll go there. So that's going to be a point on our graph. F of 2 is greater than 1, so we're going to go into there, and we get 7. Now to graph the function, we've got a parabola that's been shifted up 4. If we remember that, that's actually what we're going to kind of look at today also. But we're only graphing that parabola for x values that are less than or equal to 1. And we've got another parabola. Whichever way we want to go ahead and find the vertex, we could do the opposite of b divided by 2 times a, plug it in, or just test some points there. We're going to get this. We've got our point there. We've got a point here. And then this parabola being opening down is going to be an open circle there at an x-coordinate of 1. If we plugged in a 1, we're going to find out that that's 6, but it's an open point there because 1 is not defined for this part. It's defined there. So there's our piecewise graph. All right, let's take a look. This is lesson 1.7, transformations of functions. The different transformations there are translations or shifts. We could say either to shift or translate. So in this case, the plus 2 after the squaring means to shift up 2. So it's an upward shift of 2 units. Inside the parentheses here, that's going to create a horizontal shift. A lot of times we kind of look inside and think opposite. This is going to shift right 2. So if we think of that as setting it equal to 0, x minus 2 equals 0, and solve for x, you get x equals positive 2. So that's going to be a shift right 2 units, or a translation. They mean the same thing. Kind of in summary on the vertical and horizontal shifts, if we're adding or subtracting outside of the function, we're going to shift up or down. If we're adding or subtracting inside the function, that's going to be horizontal, left, right. Subtracting inside the function, right. Adding inside is going to go left. Those are translations, which are types of transformations. So example number 1, remember use the graph f of x equals x cubed to sketch the graph of each function. So f of x equals x cubed, one of our parent functions from our last lesson, where we would have key points at 1, 1, 1, 0, 0, negative 1, negative 1, looks like this. What is this going to do? Adding 3 outside, we're going to shift up 3. So there's our parent function with the 3 key points. All of those shift up. H of x, same parent function, x cubed. So we're going to have the same base graph, parent function, parent graph. And now we're going to shift right 3, down 2. So we're going to take all 3 points. Right 3, down 2, relocate them, redraw the graph. So make sure one thing about the parent function and the final function here is that it only changes direction of the bend once it hits this center point, which is our point of inflection. So it's bending this way, and then it bends this way. So it doesn't do a bunch of wiggles in between. Our next transformation are reflections. The one you're probably most aware of and comfortable with is when the negative is outside of the function, typically in the front, and that's going to reflect over or about the x-axis. The less common one is if the negative is inside of the function, then it's going to reflect across or in the y-axis instead. So if our parent function is f of x equals the square root of x, which we saw yesterday, and also has a key point at 1, 1. So it says, hey, here are some transformations of this. Can we write the function based off of that? All right, so here, what have we seen? We have reflected. So it would have started up, so now it's reflected. Shifts, we should always think of shifts coming last. So we've reflected. So there's the negative outside the function because we reflected across the x-axis. And then we went right 1 and down 2. So reflected across the x-axis. And then we went right 1 and down 2. There is our g of x. This one's a little bit more challenging. Probably want to simplify. Instead of going to the right, this one's going to the left. So we have reflected across the y-axis. Think of that first. So that's going to be a negative inside. And then we've shifted to the right and up. When we shift to the right, it's negative, and then that part has to be in parentheses. And now we probably want to remove those parentheses by distributing and having it look something like this. Now in mine, you will typically hear me talk about always shift last in terms of what we're doing. Be careful if you're doing any WebAssign problems, because there are some that are a little bit tricky that say something about shift and then reflect. So you really got to think of where things end up, where they're saying to shift first. So just watch out for those. All right, we've got a function. This is the graph of f of x, whatever that might be. And we want to compare that to the graph of f of negative x. We'll describe it, and then maybe show the graph as well. So we've got our negative going inside the function, so we need to be talking about that being a reflection in which axis? The y-axis. So we're going to flip everything across the y-axis. So this point, which was 3 to the right, now is 3 to the left. And we do the same thing with our open point. So there's our reflected graph. Now part B, what about this one? Got a couple things going on. We've got a reflection, talk about which axis, and we've got a shift. So we're going to reflect across the x-axis. We're going to shift left 2. So flip the point across and left 2. Flip the point across, left 2. Flip the point across, left 2. And there's where we end up. All right. Checkpoint. We've got f of x with kind of points listed here. But go ahead and sketch these 4 graphs. You probably want to do them as like 4 separate ones, not have them all laid on top of each other where we can't really see anything. But go ahead and pause here until you've got the 4 graphs. All right, so starting with this one, we're going to shift up 1. What we're going to see is that's going to change all the y coordinates. Second one, we're going to reflect across the x-axis, and that's going to change the y-coordinates. We're going to shift left 2. That's going to change the x-coordinates. And our last one, we're going to reflect across the y-axis. It's going to change the x-coordinates. All right, so the ones that we've looked at so far, shifts, whether they be horizontal or vertical reflections, are called rigid transformations. Basically means, hey, the image whatever the function that we're looking at, once we perform these transformations, it's going to look the same. It's just going to be in a different location, or maybe it's just kind of reversed like you see it in a mirror. But a non-rigid transformation is going to change the appearance. It's kind of maybe like think about looking in one of the, like at the circus or at a fair, where you look at the mirror and you're now this tall or super tall or something like that. So it changes the appearance. So those are going to be non-rigid transformations or distortions. We're talking about a vertical stretch or a vertical shrink. So that happens when we multiply our function by a constant. If the constant is greater than 1, then it's going to be a vertical stretch. If it's between 0 and 1, it's going to be a vertical shrink or compress. But this book likes to use the term shrink. So back to our library of parent functions, we've got our squaring function, x squared with the 3 key points shown. What's going to happen here? 3x squared. Since this is greater than 1 and we're multiplying, it's going to be a vertical stretch by a factor of 3. By a factor of 3. So what it does is it takes our y coordinates, because g of x is talking about y coordinates. It takes our y coordinates and multiplies them by 3. So this one was negative 1 comma 1. It's now negative 1 comma 3. We do not change the x coordinate. We multiply the y coordinate. It doesn't go up 3. It's stretched until it's now at 3. So it is here. 0 comma 0. We multiply the y coordinate by 3. It's still 0. So that point stays. And this one was 1 comma 1. Now becomes 1 comma 3. So the effect here is our parabola. It's going to get taller, get stretched vertically, also has the appearance of getting narrower. 1/3 x squared. Since that's between 0 and 1, and we're talking about multiplying, now we've got a vertical shrink or compression by a factor of 1/3. So now we take the y coordinates and we multiply them by 1/3. Negative 1 comma 1 becomes negative 1 comma 1/3. So it gets smashed down, where it has the effect of widening out the parabola. Example 4.5, graph the function. Now there are other ways, probably more efficient ways of graphing this function. Let's do it in terms of parent function and these transformations. Then we'll talk about, and basically from chapter 2, how we would actually graph this, and you probably already know from a previous course, much, much faster. So if we go parent function, we're talking about x squared as being our parent function. So we'll start there with our base graph, our parent function. And probably want to indicate key points. Then we've got a couple things going on. We've got a 2 and we've got a negative. And it doesn't really matter which of those we approach next. If we go with the 2, that's going to be a vertical stretch. So it takes our point, negative 1 comma 1, and stretches it to negative 1 comma multiplied by 2. You get 2. So that's going to stretch to here. Again, 0 gets multiplied by 2 still is going to be 0. And those are now the 3 key points. And then the negative, outside the function, it's going to flip us, it's going to reflect across the x-axis. So our key points go there. And then lastly, shift last, left 3, down 2 with our 3 key points, left 3, down 2. Key point, key point, key point. Now we want to be able to do that in terms of the transformations and also be able to describe the transformations in a logical order. And this would be something. These two we could change, make sure though if we're using the true language, we would be talking about all of it. So stretch by a factor, stretch vertically by a factor of 2, reflect across or about the x-axis, translate or shift left 3, down 2 is the full description. Okay. Now you probably remember this in another course as being Vertex form of a quadratic function parabola, where it's actually telling you the vertex, -3, -2, and then -2 being the a value. We could go right 1, down 2. If we needed more points, right 1, down 6, if we remember that from the previous course. But we wanted to be able to do this from transformations. Example 4.9. Given a function, can we identify the common function or parent function? Describe the sequence of transformations, and then use the function notation to write this function in terms of its parent function. All right, so what is our parent function? It's the square root function. So we got f of x equals the square root of x. Part B, what's our sequence of transformations to get from there to there? Stretch vertically by a factor of 2. Reflect in the x-axis. Remember, those two are interchangeable. It doesn't matter which one we go with. Shift last. Left 3. Up 5. So there's our sequence of transformations. I think this is supposed to be D. All right, so now here's the kind of the tricky part to write this in terms of that. So we want f of x to appear in the answer. What has happened to f of x? This has, so it's going to be +3 inside, +5 outside, -2 in front of the f of x. So g of x equals -2. There's our reflection and our stretch. F describes what's happening, the square root part. The parentheses x +3, there's our left 3. Closed, +5 outside is the up 5. There's our function. Example number 5. Compare the graph of each with the graph of. All right, so this one's a little bit different. We haven't really seen that one there. We could do some algebra, but if we want to just do it based on this, we're multiplying inside the function. That's actually, inside the function, is a horizontal, and it's actually the opposite of the way we think. Since we're multiplying, this is a number bigger than 1, it's actually a horizontal shrink. We don't see this very often until we get to trig functions and graphing trigonometric functions. It will make more sense there. But that is a horizontal shrink by a factor of 1/2. So we're going to take our parabola, essentially, and shrink it towards the middle. And then here, same thing, we're dividing by 5, which means we're multiplying by 1/5 inside the function. So that's going to be, again, a horizontal. But since that's between 0 and 1, and kind of think opposite here, that's going to be a horizontal stretch by that factor of 5. That's it for today. See you next time.